And to start out, because we will need these skills, I want us to review solving exponential and logarithmic equations here. So go ahead and do problem A and B. Try them out. I'm going to go ahead and give the answers for those so you can check your work. And I'll give you some minutes to try those out. Work together, help each other out. All right, let's go ahead and look at these. Remind ourselves how we solve exponential logarithms. Remember, exponentials, you want to get the exponential term by itself first. So Chris, what do we do to solve? What's the first thing? Want to add the 10 so we can get that exponential term by itself. So I have 19 to the x minus 6 equals 96. Chris, what would we do after that? Log both sides. Now, originally when we did this, we just did log and log. But I showed you guys a little trick. What would make this a little bit quicker for us? What kind of log would we want to actually use? What's the base of our exponential? If we use a log of that same base, that can help us out a little bit. Make it a little bit easier. If you do it the other way, that is perfectly fine. But if I do a log base 19, it'll make my life a little bit easier because what happens to that base 19s? They cancel out. But if I do log base 19 there, I also have to do log base 19 over here. So I have x minus 6 equals log base 19 of 96. And what is log base 19 of 96? What's our decimal, guys? Starts with the 1.550. And then what do we do? Just add 6. So answer is a 7.550. Okay. If you just do log base 10 on both sides, that is fine. You will get to the same answer. You'll have log of 96 divided by log of 19. That will still be 1.550. But this one is just a little bit quicker if we do this. All right. Any questions on A? All right, let's remind ourselves. Does anybody still need that? We're good? Let's remind ourselves what we do on B. So this one, we want to get the logarithmic term by itself. Orlando, what would I do to get that log by itself? Definitely. Let me change that. So 4 times log base 2 of 3x minus 7 equals negative 10. And then after that, divide that 4. So we should have log base 2 of 3x minus 7 equals negative 10 fourths. Now be very careful. I just want to address this. Log base 2 is a function. So if you do this, log base 2, divide, and say, oh, I'm getting rid of it. Well, that's a function. It's log base 2 of what? It has to have something inside the logarithm to complete the function argument. And so that doesn't work. What do we do instead, guys? Use the power, right? We have to exponentiate it. So to undo logarithms, we use exponentials. To undo logarithms, or to undo exponentials, we use logarithms. So I use my same base, which allows this to cancel out, and be 2 to that power. So I have 3x minus 7 equals 2 to the negative 10 fourths power. Just kidding, we can use our calculator to figure that out. What is 2 to the negative 10 fourths power, guys? So 0.1177. Okay. Yep, 177. There we go. Okay. And then what do we do next? Add 7. 7.11177. And then, so final answer 2.392. So again, we practice this, and we're going to continue practicing solving exponentials, solving logarithms. We solve an exponential by using logarithms to undo it. We solve a logarithm by using exponentials. That is how we undo those. They are inverses of each other, just like if I have subtraction, I undo subtraction by adding. That's its opposite. I do the opposite. If we have multiplying, we undid that with division. That's its opposite. Well, if I have an exponential, I do the opposite, which is a logarithm. If I have a logarithm, to undo it, I do the opposite, which is an exponential. We're doing opposite inverse operations all the way through. What we just have to remind ourselves and learn is now we have an inverse to exponentials and logarithms. They are inverses of each other. We have to be able to solve a problem like this, so we have to use logarithms to do it. Any questions on that? A little bit of review. All right, we're going to be keeping on practicing those, guys. Okay? So let's go ahead and look at the next part. So we are now, we've solved logarithms, we've solved exponentials. We want to now be able to apply these in some kind of context. Because if we just learn them without context, it's empty math. We need to say why. Why do we have this? How can we use it? So we're going to be looking at some context these next couple days. It's a little bit of a reminder. We can use the exponential form y equals a times b to the x to help us solve solve contextual problems with exponential situations. We did a little bit of that back in Unit 2A, but back then we just had problems that we could solve without the need of logarithms. But now we need to look at, well, what if we have those similar type of problems, but we have to use logarithms? So before we jump into problem 2, a little bit of reminder on this y equals a times b to the x. Our a is going to be our initial value. B is going to be our growth factor. And we actually have two options for b, because b could either be greater than 1 or less than 1. So we have that b is going to be, if we have growth, B is equal to 1 plus R. So then what would be decay? 1 minus R. So growth gives us where B is greater than 1, and decay would give us where B is less than 1. That's where that would happen. But that is a little bit of a reminder of what that is going to be. A lot of times our x value in these contextual problems, a lot of the times is going to be some kind of time amount. But if we have a times b to the x, the b is usually one of those two options. It's either going to be a growth or decay factor. So, oh, and then the last one is the y. What would the y stand for? What do we think? Something whispering over there, Jathan? Huh? No? No. Well, if a is our initial amount, after doing all those calculations, what should we end up with? An end amount, right? Or a final amount. So y would be a final amount. So thinking about all of that, I want you to set up an equation for problem number 2. What would be an equation? Read through that. Pull out your information. What would be an equation that we could have that we could then use to solve our problem? All right, let's go ahead and write the equation, and then you'll have some time to solve. So what is the different information that we're given? Again, our form is going to be y equals a times b to the x. What information are we given? All right, we have an initial value. What is that amount? All right, so 3,200. Where would I put that in? Would that be y, a, b, or x? That'd be a, right? Because that's our initial amount. So this is definitely our a. So we're going to have 3,200. Okay. What else do we have? Okay, we have y. Y is a final amount. What's our final amount? Okay, so that would go over here, 1,000. What else are we told? What was that? Our b. How do we find our b? All right, why do you know it's decay and not growth? Okay, so we can see that, right? 3,200 to 1,000, that's definitely going down. Is there another word that tells us we're going down? The depreciate, right? Depreciate also indicates that that is definitely a decay. So our depreciate at a steady rate of 18%. So B, if we're doing decay, would be 1 minus, and what is the R? The 18%, but we don't write it as 18%. What do we write it as? And 1 minus 0.8 is what? 0.82. So our B value is 0.82. And then what are we told? Anything else? Are we told anything else, guys? No, what are we wanting to look for? When will this happen? When will it have depreciated? That's definitely a time, so that's our x value, right? So, guess what you need to solve for? X. That's like problem A. You have your exponential term. You want to isolate it and solve for x. So take the next couple minutes to try that out. Solve for your x and find out how long that takes to depreciate. How many years is it? All right, Gabriel, what would I do first?
Divide by 3,200.
Divide by 3,200. Now, There was some questions out there. Can we multiply the 3200 and the 0.82? No, we cannot. This cannot be touched by anything outside because I have the power of x. Think order of operations. Parentheses exponents. I have to do exponents before I can do multiplying. But I don't know what that exponent is. And since we don't know what that exponent is, I can't apply that operation, so I can't go to multiplying. So instead, we undo it by dividing. And if we divide, that should give us, is that 0.3125? Do everybody agree with that? 0.3125 equals 0.82 to the x. Does that sound right? Okay. We have an exponential. What is our inverse operation? How do we undo exponentials? There's some people whispering it. Be confident with your answer. How do we undo exponentials? We log it, just like our problem up here. In the green there, I had 19 to the x minus 6. I undid it with the log of that same base. So I'm going to do the same thing here. I have an exponential. I undo it with a logarithm. I could use just base 10, but with our little shortcut, what base should I use? What base should I use, guys? 0.82. 0.82. You could just do log base 10. That will get you to your answer. That will be log 0.82, base 0.82 of 0.3125 equals log of 0.82 of 0.82 to the x. And I do that because what happens to those bases of 0.82? They cancel out. And I'm left with just x equal to this. Log base 0.82 of 0.3125. And if we plug that into our calculator, what do we get, guys? 0.861. What's our unit for that? Years, right? It asked us how many years. When will that happen? So this happens in 5.861 years. All right. Any questions? All right. Let's see. Let's go ahead and look at our next one. Is everybody good with this one? I can move it up. Okay, problem 3, we have some fruit flies. In an experiment, we have an equation that they've already given to us. Where t is in days, or unit of time is days. If there are 100 flies after 2 days, what is the growth rate? So what is 100? What part of that equation is 100? That'd be y, our final amount, right? So that 100 is y. What about the 2 days? T for time, right? So let's go ahead and put that in. 100 equals 33.33 E. We don't know what K is. That's what they're asking us to find. Times, oh, we know what our T is. Times 2. All right. Solve for K. Problem A here. Mandy, what would we do first? And what did you get when you divided that? 3.0. Now, if we go a little bit further, there is After there, another 3, right? But it's pretty close to 3. And if we just do 3, we will get a very, very close answer. But if we want to be a little more accurate, we go ahead and use that. I'm going to write k times 2 is just 2k. Less writing that I have to do there. Jet, what would I do next?
You natural log on both sides.
Why the natural log?
To separate e from 2k.
But why the natural log?
Because e is the base.
E is the base. Good. We have base e. If you write it as log base e, that is fine too, but if we just remember log base e is in the natural log, we have a natural log button right there on our calculator. And that base e will cancel. And Jet, what did you get for the natural log of 3.0003?
1.0986.
0986. Okay. Equals 2k. And then what's our last thing to do, guys? What do we do? Divide by 2. So now we want to pay attention. This is not our final answer. What did they ask? They asked us to find what is the growth rate. All right, there we go. That's our growth rate. But after finding the growth rate, what did they ask us to do? What does it say after the question mark? Write the population model equation. So we need to just write that equation now with that growth rate. It's nothing crazy, just y equals 33.33 e, and I can write that as 0.549 t. And that's important because look at problem B. Problem B asks how many flies will there be in 5 days? So using that model now, what would you do and how many would there be in 5 days? Let's go ahead and just do that. Any thoughts out there? How do we find how many there are in 5 days? Right, because they now have given us that t is equal to 5. We now have an equation, so y of 5, 33.33 e to the 0.549 times 5. Has anybody calculated that? 769? That's a lot of flies.